Let's convert from exponential to logarithmic form. So first, logarithmic functions are inverse operations or inverse functions of exponential functions, meaning that one undoes the other. Okay, that's what inverse operations are. So if we have a logarithmic and we want to undo that, we would make it exponential. So we can use these as equivalencies working back and forth. So the definition of logarithm that we're going to use to kind of go back and forth to show that these kind of undo each other, and that is if b to the y equals x, right? This is an exponential. Then we can also say that y equals log of x base b. And right now you're saying, I don't know what any of that means. And that's fine. But these are equivalents based off of the fact that logarithmic functions and exponential functions are inverses, right? They undo each other. So the idea is this, and this is how I always remember it, okay? This b is known as the base of the exponent, right? Y is the exponent, b is the base. Well, the base of the exponent is also the base of the logarithm. So the base stays the same. Whatever the base is, the base is. Okay, now, in an exponential piece, so I always think of it from the exponent, we have to say if we have the base b, we want to go to the other side to make it the exponent, and it equals x. Okay, this is called the argument in a logarithm, I guess because people like to argue about logs. So what I like to remember is that the argument in the logarithm is what stands by itself. So I think of things very unmathematical when I'm working through this. So first thing, as I already mentioned, base stays the same. So I remember that. And then I say, well, in the exponential piece over here, y is what is touching the base. And it can't touch the same base in both pieces. So if the y is touching the base over here, then y is not allowed to touch the base on the right. So that's how I think of it, that if y is touching the base in the exponential, y cannot touch the base in the exponential, or in the logarithmic. Okay, so let's look at this with some examples. So first, we have 5 to the third power equals 125, and we want to write this exponential function in logarithmic form. Okay, so think about it this way. First off, we know we are going to have a log. So something equals log of something with a base. Okay, in the exponential, 5 is the base of the exponential, which means it's going to be the base of the logarithm. So the 5 is done. Now, in my non-mathematical way of explaining it, 3 is touching the 5 in the exponential, so it cannot touch the 5 in the log, which means it has to be over here. And then the only thing left is 125, which means 125 becomes the argument of the logarithmic function. And then you can think about it. Well, 5 to the third power is 125, and it becomes kind of this circular motion. All right, so let's look at letter B. Again, we're changing this to a logarithm, okay? Base of the exponent, that is always where I start, base of the exponent. Then I go to the exponent itself. It's touching the 6 in the exponential, so it has to be away from the 6 in the logarithm, and that means the piece that's by itself here becomes the argument of my log. Let's do one more. 8 squared equals 64. So I have a log. The base is 8. The exponent is 2, so that's by itself. And the number by itself in the log becomes the argument. And there is my equivalent logarithmic state. Okay. A couple things to remember when we're dealing with logarithms. One is that the base must be positive. So the base has to be bigger than 0, must be a positive number. And the argument, which is this piece, cannot be negative. So the argument must also be greater than 0. So the base and the argument must be positive numbers. So if you're looking at something and somebody tries to say the log of -6 base 4 equals something, be like, sorry about you, that's not how this works in life, okay? Because the argument here is negative, and that is not allowed. So both the base and the argument of the logarithm must be positive.